Assalamu alaikum. So guys, I hope you are going great. In our previous lecture we started a topic rounding, okay, or round off technique. We started to study about rounding or round off method, uh, particularly how computer systems use rounding and why actually it use rounding. So I think you are quite familiar with what is rounding, okay, or round off techniques. But today we are going to study why we do need it in some circumstances and how computer systems generally perform rounding. So if you remember, we discussed the finiteness of resources we have in our universe. Like if we just focus or restrict our discussion scope about computer systems, so in computer system everything is finite. We do not have infinite memory, we do not have infinite storage capacity, we do not have infinite bandwidth, we do not have infinite computational power like CPU, registers, cache, clock speed, etc. So what happens, we have limited amount of resources and we need to store our information in the available, whatever available to us, and we have to perform our processing, or let's say that we should run our application, but we have a limited computational power. So our application should run properly, efficiently within the available constraints. So in this topic is a continuation of IEEE 754 floating point representation, floating point format. So in some circumstances we cannot actually or correctly store information. Like for example, if I say that we have, you want to store a very large number, floating point number, let's say that. For example, if I say that you want to store a number which is very large, let's say that, consider 2.9999 10 to the power, let's say 100, for example, or 200. Or you can say, and you can take another example. You want to store a very small number, 0.0000, let's say 15, multiply by 10 to the power minus 500, let's say that. So these two examples corresponds to very large number and very small number. So it might not be possible, okay, that you actually can store these numbers in correct fashion, in correct order, in correct format, or you can say correctly as observed by an observer, okay. So what you will do actually, you will truncate few bits, you will truncate few digits, so that you can fit as many as digits or as many as bits in the available RAM. For example, I say that, take an example, a genuine easy example. Let's say that you have a irrational number pi 3.141515 and 92. Now here you can see that after the decimal point you have 5 digits. But let's say that the system you are working, or the system you are going to work with, or the application you are going to develop cannot actually store digits beyond 4 decimal points, okay. So what you will do, you will have to skip these two digits. So one very simple technique is just to discard these digits. Very simple technique. Okay, but what will happen actually if you discard, the last bits or last digits, okay, which cannot be stored in the available RAM or available storage cell. So you will get inaccuracies, okay, in your calculation. And if you remember, I always give example of Patriot missile failure. One of the reason of Patriot missile failure was rounding, if you remember. So we have to devise a systematic technique so that the effect of rounding should be minimal. Definitely there will be an effect, okay, but we try to minimize the impact. We always try to minimize its effect. So the technique which we generally use to escape last digits or last few bits, if we are considering binary representation, is known as rounding or round off method or rounding technique. Okay, so here you see two things in red, two keywords, two words. One is approximately and one is exactly. Let's say that I give you an example. You are an observer, okay, and you are observing the position of Earth related to Sun, for example. And let's say, let me draw it, because I always like drawing things so that concept gets clear in easy way. Otherwise you just start thinking and I don't know what runs in your mind. Okay, so we have considered this. Give me a second. Let's say that use this color. This is our Earth, and I'm just drawing it for the purpose of demonstration. This is Sun, and you are, I don't know how you do that but let's assume that you are observing the position. Sorry, give me a break. Let's say that you are observing the position of Earth, right, relative to Sun. And you know that, for example, if you monitor or observe the position of Earth, let's say that in 24-hour interval, so definitely there will be a measurable change in the position or the velocity or a particular, it might possible that it will go in this direction or maybe it will go in this direction. But let's say that if you are observing the position of Earth every 1 second, so the change will be so much small that you may observe correctly, considering you have very sophisticated equipment or tools available to you for the measuring the position. But the point is, let's say that 1/6 into, let's say that meter. This is a change every 1 second in position, and this is just a distance I'm mentioning. I'm not mentioning the position or the velocity at the moment. I'm not considering direction, just for the purpose of simplicity. So you have observed this change okay, from the previous position of Earth. But the problem is you cannot, give me a second, what happens? But the problem is you actually cannot store, this value in a floating point number or a double precision floating point representation, because the floating point number, if it is 32-bit, or double floating point number if it is 64-bit, you cannot actually exactly store this number, this observed value. So what you will do actually, you will make an approximation. So the objective of rounding is we want to make our approximation as correct as possible, as actual as possible, as exact as possible. So this is the purpose of rounding, right? We are going to approximate things. We have a number, we have a floating point number, but we want to approximate it. We want to truncate few bits, we want to truncate or skip few digits if it is decimal number, but we want that we should not miss too much detail, right? So the process is rounding. Rounding is a systematic approach to perform this activity. Alright, so I gave you this example also, if you remember, okay? So before giving this example, I think we should discuss the 4 types of rounding techniques available to us in computer system, and I would like to discuss these 3 techniques first, and then we will come to the first one. Round towards 0, round down, round up. As you can see that from their names, round towards 0 means that let me draw it a number line over here. So this is the number line, and assuming this is 0 over here, then I say this is 1, then this is 2, then let's say this is -1, and let's say this is -2. Now what we have, let me change the color as well. Give me. Okay, now for example, let's consider the first type of rounding. First means here the second, round towards 0, and we got 1.40 and we want to round it. So round towards 0 means if my number is positive, I have a positive floating point number, so round towards 0 means it will tends to move towards 0, and if my number is negative, then again it will tends to move toward 0 from the left hand side. So if I got 1.40, as you can see here, so 1.40 may lie somewhere over here. This is 1.40, okay, and if I round it, it will convert into 1, because my goal is to move toward 0. Similarly, 1.6, 1.5, 2.5 eventually will round to nearest integer. And here you can see that if I got negative number -1.5, it will lie somewhere here, -1.5, so it will become -1. A very simple approach. The second approach is round down approach. In round down approach, my target is to move toward a lesser number in magnitude. I got 1.4, it will be converted to 1. 1.6 converted to 1, 1.5 converted to 1, 2.5 converted to 2, and minus 1.5 converted to minus 2. Why? Because minus 1.5 is greater than minus 2, and my target or my rule is I want to round down. I want a smaller number, so I'll rather go toward minus 2 as compared to minus 1 in the, as you can see in the previous example. Round up, a scaling approach. Okay, whatever you have, you are going to scale up. Alright, so if I got 1.40, it will scale up to 2, 1.6 to scale up to 2, 1.52, 2.53, and here again minus 1.5. Now here it will be converted to minus 1, because minus 1 is greater than minus 1.5. Right? So these are the three very basic techniques or rules to perform rounding. However, the default technique, as we discussed in the class of rounding, is round to even. Okay, and this is the default technique in if you are using IEEE 754 floating point format, and in most systems this is the technique which is commonly used. So let's see what is round to even. Okay, and so in order to study round to even, let's consider this diagram, right? And I think this position, I got it over here, this is the center. I can say that it is 0. Okay, let me change the ink color. Alright, so let's take few examples over here. Let's say this is I think take it as some other number so that we can consider it is not 0. Let's say that consider this position is this, the pillar is 1. Okay, the second pillar corresponds to 2, and this bar corresponds to 1.50. This is 1.0, this is 2.0, and this is 1.5. Now take few examples. If you are standing here at this position, okay, and another example, let's say that you are standing over here. For example, this is 1.3 and this is 1.8. Now assume if the bridge has broken, it is collapsed from the center, from this position. Okay, and if you are standing over here, what you will do, you will run. Obviously, first of all, when you will run, so whether you will go toward this side from where the bridge has broken, or towards this side, which distance is the smallest one? For this position, for 1.3, let's say if this is position number A, and this is position number B, and this is position number C. So if you are standing at position number A, you will definitely run towards left hand side, right? And for instance, if you are standing at position number B and the bridge has collapsed from the center, so you will run towards right side, so that you can quickly secure a safe position. right? So what will happen if you are okay, I'm talking about round to even approach. So what will happen, so let's say if you have 1.3 and if you have 1.8 and you just want to round it down to one decimal, with I mean I will say that without decimal, just no, with no decimal figure. So this 1.3 will be converted to 1 and this 1.8 will be converted or round to 2. Very simple technique. You will choose the nearest integer. So for 1.3 the nearest integer was 1.0. I mean nearest integer means because this is a floating point number, so technically there will be no integer, but when I say that the integer, it means that I'm talking about the mantissa. Okay, all right. And if you have 1.8, so definitely you'll choose 2. Very simple approach. But the problem will come if you are standing at 1.5, center of the bridge. So you have both the options, whether you will run towards the right side or you will run towards the left side. You have both options with equal probability. So here you have to make a decision and you have to follow a rule, and that rule is round to even up rule. Okay, and let's see in a moment. Okay, so you have to read this one, half values. So let's say if you are standing at the center of the bridge at 1.5, okay, so round off the number either upward or downward such that the least significant digit of the result is even. So this is the point, you need to note it down. Least significant digit of the result is even means after rounding the LSD, or you say that least significant digit should be even, not odd. We'll see. So these are few, I think, simple examples. Round decimal numbers to the nearest hundredth means I want 1 point or x. I mean I want 2 digits after decimal. So I will have to truncate, or I have to round off these 5 digits, and again here these 5 digits. So since the first example 1.234 and then quad 9, here the halfway will be, for both the cases the halfway will be this 50,000. Okay, so this 4 and quad 9 is less than 5,000, and 5,001, not 5,000, 50,001. If I just consider if I just read these digits, 50,001 is greater than 50,000, obviously. So these two numbers are not at halfway. So apply a very simple rule. You just, if the number is at the left hand side of the bridge, as we saw in the example, if a number is at position A, you will round towards left side, and if a number is greater than halfway, then you will move up or scale up towards the right side. So this number will be round off to 1.24, sorry 1.23, this number, because this is less than halfway, and this number, since it was greater than halfway, so this digit will be round off and updated to 1.24. Okay, so this example was very simple. The problem will come when we have a number which is halfway. like here if I got 1.23 50,000, I mean 5 and quad zeros, and second number is 1.24 quad zero. So I have mentioned that both the numbers, okay, will be round to 1.24. Now we have to study how and why. Sorry. The technique is round to even. You need to remember the LSD, don't confuse with some other thing, least significant digit, or if you are talking or considering a binary digit or binary word, so it will be LSB, least significant bit, should be even. Alright, so here you have to discard, let me change the pen in color, so here what we want to do, we want to discard all the 5 digits but after rounding. So the technique is round to even. The least significant digit or least significant bit should be even. So since both the numbers were halfway, so this is odd, 3 is odd, so I have to make it even, so it will be round to 1.24. However, 1.24 and then 5 and quad zeros, here the least significant digit was already even, so there will be no change. This approach or this technique is known as round to even approach, and this is the default rounding technique in IEEE floating point format representation, and most computers our systems use this technique by default. Now you may ask, why this technique, why round to even? Okay, so the answer is statistical bias. Okay, let me let me discuss what is statistical bias. Why not consistently round values halfway between two representative values upward? Now the thing is, there are few arguments. Okay, why you do not want to scale up all the time? Okay, if I have got, like in the previous example, 1.23, so I should scale up to 1.24. Why I did not scale up, especially for 1.24 scenario, the second scenario? The reason is the average of set of numbers that we rounded by this means would be slightly higher than the average of the number themselves. Let's say that I have set of numbers right now. Let's say I'm taking 3 numbers like 1.235, 1.245, and let's say 1.23, sorry, I should say 1.275. Now what I'm trying to say, that if all the time if I round upward, okay, if I scale up the number, so the average of all these numbers, when I after rounding, if I take the average, that average will be slightly higher than the average of the actual numbers. Similarly, if you say that okay, don't if that is the scenario, don't round upward, go for round downward. Okay, so in that scenario, the average will be slightly lower than the average of the numbers themselves. We can, I think we can, I can show it what I'm trying to say. That for that I have to, let's say that we take few numbers 1.235, 1.245, and 1.23, no, 375. Okay, and I think that's enough. That's okay. And if I use Excel, I have to use, in order to show statistical bias, you have a large data set, but just for the purpose of explanation, I'm taking only three numbers. So maybe you will not see uh, a clear indication or clear difference, but at least you will get the idea. Okay, so let's say that you have these three numbers. Let's take two more numbers. Let's say 1.295, and let's say that the last number is 1.285. So you have got five numbers. Okay, so if you take the average of these five numbers, okay, let's say that I would like to use the I don't want to use average function. I don't know how it works in Excel, so I prefer to add individual cells and divide by 5. So the average of these number is 1.267. All right, so this is the average of the actual numbers. So if I follow an approach of round upward, all the time I go for round upward, so this number will be 1.24, this number will be 1.25, this number will be 1.28, this number will be 1.2, this number will eventually move to 1.30, and it will be 1.29. okay, so let me copy this formula and paste it over here. Now you can see that there is a difference. Okay, obviously you'll get a difference whenever you are rounding a number, and if you are going to compare that number with the original number, so definitely you'll get a difference. But here you have a very small data set, so the difference will not be very effective in terms of accuracy or correctness. But you will see that here you got a difference, and the difference is about in this scenario, let's say this is the greater than, so I should write it. So you get a difference of 0.005. So this is I think this is a big difference. And if we we take downward approach, okay, whatever we have, we downward, so we are going to scale it down. Okay, before going to scale it down, let's check the result with round to even approach. Okay, even. Okay, so if I got this number, okay, so 1.235 will remain 1.23 because it was not even. Am I right? Give me a second. So 1.24 remain. Okay, 1.23 should be converted, odd should be converted to even, and even should remain even. So it will be 1.24. okay, and 1.24 will remain 1.24, 1.28, then 1.30, and 1.28. Now I guess this will be the result. Here what round to even says, if you got an odd number, it will be converted to even, and the even will remain even, right? The even will remain even. Here 4 is even, so the 4 will remain same, but 3 was odd, so 3 is converted to even. Okay, now here we got 1.235, so this 3 is odd, so we change it 1.24. 1.245 converted to 1.24, 1.275 converted to 1.28, 1.295 converted to 1.30, and finally 1.285 remains 1.28. Now let's do it. I don't know what will be the result, I mean the difference, but let's do it. This is 1.26, so alright, so you can see that the statistical bias or the rounding error here is very less than as compared to if we go and apply upward rule. Similarly, you can try it with the downward rule and you will observe a statistical bias. So in order to reduce the statistical bias, or rounding error is something different, it always happens, but in order to avoid previously I mixed the statement, rounding error will be always there. So in order to reduce or eliminate or minimize the statistical bias, we follow round to even approach. If we do not follow round to even approach, if we go with round upward, round downward, we will have a lot higher statistical bias, right? You can say that statistical bias is also a rounding error, right? Alright, so I guess that was clear. Okay, special properties of IEEE encoding QA discussion in next class. Okay, so in the next class we are going to have a discussion on special properties of IEEE encoding and a QA discussion next class. Floating point 0. Now the thing is, if you remember, as I told you earlier, that EXP field, if you remember the EXP field in IEEE 754 format, we use a very different approach to encode EXP. We introduce a term, a formula, and we introduce a new concept of bias. Rather, we can encode it with the help of 2's complement because it could have positive and negative numbers. But remember, we introduced that very complex new thing. So the benefit of introducing that logic or that format is we can apply same FP floating point 0 same as integer 0. If you see that if you have got a number which is integer and you get a 0 in integer, so it will have a same bit pattern for floating point 0. Similarly, we can apply same comparison operations of integers over if we have a number which is encoded with floating point IEEE 75 format. So there are few things that I think we'll see in the discussion session on Monday, and I guess couple of things are left in this chapter, and I think it's about operations, last couple of topic, floating point operations and floating point in C. So these two topics are left. So I will suggest you to at least go through these topics, floating point operation and floating point in C, floating point techniques. So we can have a sort of QA session and I would like to hear from you guys so that we can conclude this chapter. uh, and one important thing, as if you remember, when everything was working fine, I think, when although we were having online classes at that time also, I told you that we would like to have the practice problem of discussion on practice problem of chapter number 2, which is very important. So I think, I don't know whether we will able to do that. If we finish, sorry, this is, if we finish floating point representation operation everything on Monday, then on Thursday class I would like to have a session on practice problems of chapter number 2. And as I always, I think I already gave you this task, so solve all the practice problems of chapter number 2, so that whenever we finish chapter number 2, whether on Monday or in the next lecture, we have a complete 1 hour, or depending upon the situation, one session on practice problem. So it will be a sort of not a proper quiz type of thing, but it will be like I will ask you, anyone, okay, to share your screen and explain the, let's say, that problem 2.5, 2.6, 2.10, etc. So be ready for it. We will have almost a week now. It's late Friday night, early Saturday. So we would like to have practice problem session on in just after finishing this chapter. Thank you. I'm stopping the recording. I'm going to post this recording now shortly, and if you have if you watch this recording over weekend, and if you have any queries regarding this this concept, so you can ask me via forum post. Don't wait for Monday. In fact, we will discuss your questions on Monday. We'll take few questions, but it's nice if you can post it on forum and you can have a chatty discussion, right? Thank you. Take care.